So we should get started right away here. You guys good? You guys remember playing Angry Birds? Is that even a thing anymore, or did that phase out years ago now? Yeah. You guys remember playing this game though, right? Like it was massive for a while, probably when I made these notes. So what we're going to talk about today is a projectile, where I mean, here's the definition basically. The only force acting on the projectile is going to be gravity. Once it's in motion, it's going to stay in motion in the x direction for forever, because the x direction really has no forces acting on it. So if you kind of broke the projectile up, there's always going to be an x direction going forward. But in the y direction, gravity's acting on it, right? Turn your noise down a little bit here. In the y direction, gravity's pulling it down, right? And so at first, okay, well, it's got a certain amount of y direction going up. But then the amount of y direction is a little bit less because gravity's pulling it down. Right at the peak, the apex, the vertex, if you know that word, of this parabolic shape, really the y direction, there is no velocity, right? If it hadn't been going forward, if I just threw, well, I won't throw this pen over from this. If I just threw something straight up in the air, right? For a second in the air there really is no velocity. It's, yeah. Anyways, and then on the way back down, it's going back down again. So today we're going to work on some math behind the projectiles, things that are in the air. For those of you who are on the second assignment, this is where we're going to talk about how to do the question where like Tom Brady throws a touchdown. Okay, I've mentioned this before. So we can technically do x, y, and z directions. We're just going to do x and y. Okay, so we don't actually really worry about the swivel angle in this course here. Other thing I have here is that we want to make sure that we try to notate things really importantly. So you want like velocity initial in the x direction or like distance in the y direction. I think it's really key to make sure that you're specific on those things. Last one here, this is the key to the whole thing, it's the linchpin. Time is independent. Time doesn't matter whether it's in the x or y direction, because really time is not a vector quantity, right? Time is scalar. Before we get to the examples, just some more talking pieces. Velocity should remain constant in the x direction.
Mr. Petluck, can you please come to the office? Mr. Petluck, please come to the office.
The y direction, you can actually have a change in velocity. So in terms of like what I've written here, you can have a velocity initial in the x direction, a velocity initial in the y direction, distance x, distance y. But really acceleration only applies to the y direction, because gravity pulls things up and down. Gravity doesn't make things go faster in the side-to-side direction. So we really only have to worry about acceleration in y. Time, and then we're going to throw in one new variable, which we haven't really covered yet, an angle. The angle being the angle at which you launch something. If I throw something at a very steep angle versus a more shallow angle, that's going to make a difference. Does anybody know what the most optimal angle for launching something is? 45, yeah. If you throw something, let's see if I can find multiple things to throw here. These look safe. If I throw something just at more or less flat, right, 0 degrees, we'll go that far. If I throw something straight up and down, this would be like at 90 degrees. If I actually let it fall, it really didn't go that far at all, right? But if I want to launch something the furthest, if I want to get to this side of the classroom, I have to aim for like a 45-degree trajectory, and that's what will get it the furthest. As soon as you go above 45, it starts just going up only, right? And if you aim below 45, it won't have enough launch distance to actually get somewhere. Does that make sense? All right, what else do I got before the examples? I think another picture here. Yeah. You guys ever watched the good old Wile E. Coyote Roadrunner cartoons, right? The classic, he runs off the cliff and he stands there for a second and looks down and then finally gravity takes hold. That's not really true, obviously. That's cartoon physics, right? So just a reminder of what's going to happen. As soon as he leaves this, yes, he's got a forward trajectory, but immediately gravity is going to start pulling him downwards. It's like, well, first there's going to be a little bit of y velocity along with your x velocity. Then there'll be more y velocity with x velocity. Then even more. Actually, that's convenient as you go forward. Does that make sense? And you'll eventually start going to the point where, really, are you still going forward? Yeah, But really, most of the velocity you'll have then will be pulling you straight downwards as gravity accelerates you more and more. Another picture just to illustrate the same concept here. If you were to say like slide, I don't know, anyone ever play shuffleboard or something like that? Slide something across the table. It's not going to keep going on this trajectory for forever because gravity will eventually pull it down. But does it land right here at the base of the table? Well, no, because it's still got that forward X momentum. Similar picture. I feel like I've made my point. Have I made my point well enough? Okay, let's do an example. So here's where the meat of the lesson is. I think I have like 5 examples. And hopefully with these, I can illustrate a sort of bunch of different, I don't know, things that you're going to need when we solve questions. So here's our first one. A hunting rifle, I looked this up, can shoot a bullet as fast as 350 feet per second. So there is our velocity. Here's the issue though. Who here hunts? Anybody hunts? Yeah. You have this issue. I talked with Justin Delver about this 2 years ago in physics. When you shoot, the bullet is going to have a little bit of a drop factor because even though it's traveling really fast, more or less in a straight line, it is going to drop a little bit due to gravity. So you have to compensate when you shoot. Is that something you have to work on? Yeah. You know what I'm talking about that, right? So if you shoot straight, you might miss your shot because the bullet is shot along a flat trajectory, but it actually might go downwards a little ways. Let me see if I can draw this a little bit better. Here's a person with a gun. I can't draw very well, so it's a handgun today. And they try to aim at what they think is their target, and they draw it straight. Come on. This new board is taking me over to get used to. They think they're shooting it straight, right? But even though the bullet is traveling really fast, okay, what's actually going to happen is the bullet will, I'll exaggerate it, will sink. Does that make sense? And if the target that they're aiming for was right here, for example, they thought they were aiming for here, but the bullet would actually hit there. Right? So anyways, let's try solving the question with the variables we have. So this one right here, I actually am asking you, when will the bullet hit the ground? So not just like how much of a sink would it have, but how long would it take for it to actually reach the ground? So I'm going to start by writing what variables I know. I know my velocity initial in the x direction is 350 feet per second. That's the first thing I know. It also gave me a trajectory of 1.3 meters above the ground. In a way, that's how much y distance this thing is going to need to fall. It's going to have to fall 1.3 meters. Makes sense? Because in the up and down direction, that's how far the bullet needs to fall. Those are the only 2 numbers I was given, and yet there's way more information implied. So let's try a few of them. What would your velocity initial in the y direction be if you just shot the bullet straight? 0. If you shoot the gun straight, you're shooting with purely x velocity. It's almost like you're dropping the thing. Does that make sense? I mean, you're not, obviously, right? But it's like it has no initial y velocity. So there's another piece of implied information that we can use. What else is implied that we can use? Good job. Acceleration due to gravity, and again, in the y direction. Now, we've got to make sure we get our positive negativeness correct. If I'm going to make my distance that it falls 1.3 meters a positive number, then let's make the acceleration also positive 9.81, just because it's going the same direction. But if you were to shoot the bullet up into the air and gravity pulled it back down, then make one positive, one negative. Does that make sense? Okay, let's talk about some other variables that we don't know. What we don't know is time. Tell us nothing about time. We're also looking for the distance traveled in the x direction. These are some things we're looking for. This velocity initial in the x direction, is it ever going to actually change? Is there going to be a different final velocity in the x direction? Or is it just going to keep traveling that 350 feet per second for the rest of its ability to? You know what I'm saying here? This velocity initial in the y direction, if I were to draw the bullet, it's going to go like this. Then it's going to go like this, but down a little bit. And then like this, and down a little bit more. Then like this. Oh, we can't go straight. Like this, and then down even more. And that's going to cause it to eventually fall. But in the x direction, would you guys agree that that velocity is always going that speed? In the y direction, though, really it starts with no velocity and keeps going down. So we're going to have to start with the y direction. That's the one we're going to start with. Because in the y direction, I have 1, 2, 3 variables. If you ever have 3 variables, it's enough to solve. And what we're going to solve for is time. Because does time really depend on a direction? Time's independent. So here's where we start then. We're going to see how long it takes the bullet to fall based on our y direction information. So the distance this bullet will fall in the y direction will be equal to the velocity initial of the bullet in the y direction times time plus 1/2 of the acceleration, again, in the y direction times by t squared. Thank you. You still need Donatello?
I'll leave it on.
At this point here, hopefully you guys can just plug in the values I need, right? The distance it's going to travel is 1.3 meters. There is no velocity initial in the y direction. Right? Essentially, from the y direction's perspective, it's like you're dropping the bullet. Right? Which is why actually casings will fall at the exact same time as the bullet itself will. If you actually set that up, you know how sometimes it ejects a casing and it just falls? It will actually hit the ground at the same time the bullet will. Essentially, they're both just dropping. That's all 0, so you need then 1/2 of 9.81 meters per second squared, and you need your time squared. So just solve for t now. I'm gonna go grab my calculator. So the bullet has to fall 1.3 meters times by 2 divided by 9.81 square root. I would recommend get into the habit of doing either one of two things. Once you find this value for time, we are going to need to use it again. So option 1, write down every single digit you can. So here's what I've got, 0.5148161593. You guys get that value as well? Yeah. That's option 1. Make sure you write down all the digits because we're going to need them in further calculations. Option 2, when you use your calculator, store it as like either A or B or C or something like that.
How do you store it again?
Sure, let's show that. So you got your calculator. You just finished doing, what was it, 1.3 times 2 divided by 9.81. You've square rooted your answer. Okay, so you got to this point here. STO right here has an arrow next to it, so press store. It's going to take your answer and store it. You just have to define a letter for it. So go like alpha, and then pick a letter. I'll just go with A, right? From now on, whenever you type in alpha A, that value is all they're waiting for. But we're at the point now, and we got it after, you know, just a week and a half or 2 weeks of physics, where you're going to have to make sure you keep track of numbers because we're going to use those consecutively going forward. So don't round it. Don't use 0.51. That's going to cause issues. Okay. So far, so good. We know how long it's going to take this bullet to hit the ground. Well, in the x direction, the bullet is always traveling consistently, really. The only reason the bullet stopped is because it eventually hit the ground. Right? But it's traveling a constant velocity. So in the x direction, we can say the velocity in the x direction is equal to your distance in x over your time. We don't need to worry about the initial or final velocities because really it's always going the same speed going forward. So I know I wrote this was a velocity initial in x, but really it's just the velocity in x. It's always going that direction. One more thought. I know this is in 350 feet per second, but I'm just going to leave it that way rather than converting it. We'll just have an answer at feet. That's all. You travel 350 feet per second. We want to know how far it travels in x, but we know that this time value is coming from right there. So use that exact number to times by 350, and that'll tell you how far the boat will go. I got 180. Just the units are in feet, that's all. The link, the bridge between these two things is time. Almost always is. I can't really think of an example off the top of my head right now where time is not the link. So you use one dimension to solve for time, and then that time is also the same in the other dimension. So, last step, we should do proper sig digs. I believe we only get 2. So our time would have been 0.51 seconds, and the distance the bullet would travel would be 1.8 times 10 to the 2 feet. So far, so good? Awesome. Okay, another example. You guys ever been to Head Smashed in Buffalo Village? You must have at some point. I actually haven't. I hope that's really strange, so I never have been. So you maybe you've heard this before. Blackfoot people traditionally used to take buffalo, herd them over the side of a cliff, and then they would die by falling off a really big cliff. Essentially, the picture would look something like this. They're just like our bullet. They were traveling on a nice flat trajectory, right? And then after a while, they're going to do that. That picture makes sense? So we're doing the same sort of thing. We want to find the distance from the base of the cliff where they'll land. So we're looking for we're looking for how far from here to here will the buffalo, as they're herded off the cliff, eventually fall. Kind of like the shuffleboard picture I had earlier. So let's give it a try. We need to know some variables. 20 meters tall. What is that? Distance in y, 20 meters tall. The bison are moving at 18 meters per second. Good. And I can probably skip the initial in the x direction, because really that is the speed they're always traveling in the x direction. They're not going at speed differently, right? Okay, that's all we were given. But we can work with this. The velocity initial in the y direction, again, was 0, just like last time. Unless the buffalo, like, say, jumped as they got to the edge of the cliff, that's just, they were basically falling. And our acceleration in the y direction, again, is 9.81. Honestly, this question is the exact same setup as the last one. It's really hardly any difference. See how I've got 3 y dimension values? As soon as you've got 3 values in one dimension, you should be able to solve for the 4th. So we're doing the same thing we did last time. Velocity, what is it? D equals VIT plus 1/2 of AT squared. All of them are y directions. Gonna fall 20 meters. They have no initial velocity in the y direction. Essentially, they're falling. And then we need 1/2 of 9.1. Cannot get used to this head yet. Times 2 divided by 9.81, square root of the whole shebang, do it properly. About 2.0 seconds. I'll write it out, 2.0. Let me know if I did it wrong. You guys get this right? Awesome. Okay, and then the link. Remember how I mentioned before that sometimes what we need to do is we need to take 2 formulas and merge them together? That's essentially what we're doing here, is we're taking one formula solving for time, and then immediately plugging that time into a second formula. So I'm just doing it in stages. So then in your x direction velocity is your distance in x over your time. Time doesn't actually need to be a variable for x or y. We knew our x velocity though, right? What was it? 18 meters per second. Yeah. Second, there we go. It equals our distance in x over this time, which we just solved for. Just multiply. So final answer I got was 36. We get 3 sig digs, so make sure you keep all your units all the way through, like every single digit. Don't lose precision. I got 36.3 meters. So far, so good. Okay. Both of those examples were really the same thing. The first key to them all was that our initial velocity in the y direction was 0. So that's great. Every single time I have a scenario that looks like this, I've got it nailed. What if it's like, remember how you guys were looking at that bus example the other day there, where that bus seemed to like launch? Well, what happens if something has, I think it's the throw here. What if it launches with an angle, right? Right. So what if Tom Brady is going to go throw his touchdown? Or what if an NFL punter is, oh my goodness, I'm having a bad week. What if an NFL punter is punting a football, but it's at a bit of an angle? So I've actually got a lot of different components for us to look for here. So this example is really going to cover multiple things. So let's draw a picture here. An NFL punter is going to kick a ball at a speed of 17 meters per second, and I'm going to give you an angle though. The angle is 60 degrees above the horizontal. So a bit of a picture here. Here's the punter. He's going to kick the ball with his foot. There's the ball off of his foot. And it's going to go, where'd my cursor go? It's going to go like this, right? It's forward. Huh. I cannot see the mouse anymore. That's not good. It's like I'm destined to not be able to teach with my little board anymore. Okay, let's try it again. Let's see whether it's working again now. I should sit to do this. Okay. Wait, take 2. Let's try that again. So punter guy again has the ball. He's going to kick the ball off his foot. Not to scale, obviously. And it's going to do this, right? Everybody good so far? You might notice that this time I didn't give a whole lot of numbers though. You've got 17 meters per second and 60 degrees. So in a way, it's almost like we need a triangle at the very, very beginning of this thing here. And in the corner of this triangle here is 60 degrees. Where would that 17 meters per second go? Is it the x velocity? Is it the y velocity? Or is it the hypotenuse? It's the hypotenuse, yeah. Like on this little triangle that I'm kind of making right here, right there, that's the 17 meters per second on the edge there. I'm going to say it again. So in a way, here's the information I have. I have an angle. The angle is indeed 60 degrees. I have a velocity, but I'm going to call it the resultant velocity, is 17 meters per second. I don't actually know the x or y velocities. I get to know what the hypotenuse over here is. Okay. This is getting challenging. I don't actually know where my cursor is anymore. Oh my goodness. Okay, there. Now I can see it. Okay, so let me try drawing this like triangle in here to begin with, because this is what we're gonna have to do. I'm gonna make a bit of a triangle here and set the hypotenuse 17 meters per second, and the angle right there is 60 degrees. What we need to look for then is the velocity right here, initial, in the y direction, and the velocity, oh my goodness. Sorry guys, this board is driving me nuts. I cannot see. You guys see what my issue is here? I don't know where the mouse is anymore. Like it's not showing up as I move around. So that's why I'm struggling so much here, because I don't know where the cursor is. Okay, and so we're gonna look for the velocity initial in the y direction right here. And right about here, the velocity initial in the x direction. We need to find those, because there's going to be some upwards component to this fall, but there's also going to be some forward component to this fall. Does that make sense? Okay, where's my cursor? Put it there. So, to figure out, for example, the velocity initial in the y direction, any idea how we're going to calculate the upwards component? Yeah, SOHCAHTOA, exactly, yeah. What we could say is, let's see, I guess it's about there. The sine of our angle would be equal to our opposite over our hypotenuse. So the sine of 60 degrees would be equal to our opposite, which is velocity initial in the y direction, divided by the hypotenuse, which is 17 meters per second. And that'll get us our initial velocity in the y direction. So I just got to take the 17 and times it up there. So velocity. This is frustrating. Oh, so frustrating. Maybe you just can't handle being on full screen. So this is the opposite right here. As soon as I write, it takes the cursor away. That's the problem. And then this right here would be the hypotenuse. Here's going to help me out because I am having a hard time being able to write here. What's 17 times sine 60? 14.7. And you're going to save all those numbers, right? So 14.72 meters per second. Okay, we have to do the exact same thing then and figure out how much initial x component does this ball have, right? Because it's not only being kicked up in the air, it's being also kicked forward as well, right? So the math is really the same there. It's just rather than using sine, you're going to use cosine. So I'll try writing that down here. Cosine of theta would be the adjacent over the hypotenuse. That would be cosine of 60 would be, let's see, the adjacent would be the velocity initial in the x direction over 17 meters per second. So velocity initial in the x direction, help me out here. Where do you get the value? 2.5? 8.5. 8.5. Okay. Let's see. That looks like it's about there. 8.5 meters per second. Okay. I'm buying a new board tomorrow. I'm returning this one. Okay. Other things we know. We've actually used all the numbers they gave us. We used our angle and we used our initial velocity. We managed to break it up into an x and y component, but there's other stuff we know. For example, about here, about there. We still know the acceleration in the y direction. What's it going to be? Okay, which number are you going to use? Good, that's what I was hoping to hear, the negative. Y negative 9.81. Why negative? Good, you got it, awesome. Okay. Okay, so that's actually enough to kind of start us a little bit here. Let's now go and answer what our question is. So the first question is, can we find the vertical and horizontal components of this velocity? I think we've done that, right? We know how much up and sideways we've got. Now we want to find the maximum height the ball will reach. So I want to talk about this location here. What's going to be unique about this apex, this vertex? There's one more variable that we know at the very, very peak of the jump. For the y direction. Good job. Yeah. We know that the velocity final in the y direction will be 0 at the peak of the jump. Right? This is only temporary, right? But at the highest point it reaches, the y direction velocity essentially is at that stop spot. So we now have enough information to, where's the extent of there it is. We now have enough information to solve. So we're looking for the distance in the y direction at this point. So this is the same formula we've been using for a while, isn't it? D is going to equal to VI in the y direction. No, that's not the right formula. That won't help. What do we have? We have velocity initial, velocity final, acceleration. We need this formula. Velocity final squared equals velocity initial squared plus 2AD. So bring this to around there. 0 will equal 8.5, whatever that number was. Squared. Oh, good catch. Nice guys. The 14.7 number. Oh, today is just not my day. Not my week, really. Velocity final squared will equal. No, could be better than that even. 0 equals 14.7 meters per second. Square that value. Plus 2. Okay, don't forget the negative though, right? We need that negative number. Negative 9.81 times d. I might have to shorten up what I write on the board here. It's being a challenge for me. You guys okay with being able to handle that? Stop me if you're not.
Why are we using 14.7?
Because that's our y initial velocity. What we're talking about is in the y direction, it started going up with a certain speed, and at the peak of its jump, it would have then stopped before coming back down in the y direction. Does that work? You need that to be a negative 9.81 because when you're going to divide the you'll bring the 14.7 squared to the other side, right? It's going to become a negative number, so you're going to have another negative number to divide by it. What did you guys get when you calculated this? 11.25? 25 meters. Oh my goodness. Let me do this. Okay. We should finish with sig digs here though. With sig digs, I get 2. So it will go 11 meters in the air. That part okay? Alright, next one. We now want to know the length of time the ball will be in the air for. I'm going to show you guys a neat trick. If we assume that the kicker is basically kicking the ball off the ground, the ball will go all the way up in the air and then come all the way back down. How much distance in the y direction will the ball actually travel? The ball is going to start on the ground, go all the way up in the air, come all the way back down. How far will the ball have traveled in the y direction? 0. Because it started on the ground. I know it went all the way up and all the way back down, but from start to finish, the displacement, I guess is the word I'm looking for, right, is really 0. So that's a neat trick we can play on the next one here. The ball will be in the air, but in the y direction, the ball really will have traveled no distance. That may sound strange, but let's go with it.
Wait, could you just say again?
For sure. Okay, so we're going to, what can I throw? I'm going to objects throw. Right? The ball is going to get kicked up in the air and come back down again. Right? I want to know the length of time, the distance this thing has traveled, like the displacement it's traveled. I know it's gone all the way back up and back down again, but hasn't it traveled a net of 0 meters? Because in the y direction, it started here and it ended here. That makes sense. So from the y perspective, we now know that the distance in the y is going to be 0 meters, just 0 meters. Sorry, we don't need that line after it. The distance in the y will be 0 meters. We're looking for time. Sorry. Time. The velocity initial, we have the velocity initial in the y direction, right? That was 14.7. And the acceleration was negative 9.81 meters per second. Let's try sitting again. I think I'm better with this when I sit. I'm so sorry, guys. This is not an ideal scenario. Okay, so distance in the y direction will equal the velocity initial in the y direction times time plus 1/2 of the acceleration in the y direction times time squared. How much distance in the y direction is this thing going to travel once it's gone all the way up and all the way back down? In terms of displacement, it's traveled nothing. So, okay, good. 0. Velocity initial in the y direction? 14.7. Okay, so 14.7 times by time. We're going to need to add 1/2 of our acceleration, but our acceleration is negative 9.81, and then t squared. What do we need to solve this? Good old quadratic formula. I'll do my very best to write this down neatly, but you guys are going to have to bear with me as best you can. Okay, so our a value in the quadratic formula from right about here is going to be 1/2 of negative 9.81. 1/2 of negative 9.81 means my a value will be negative 4. I think it's 905.
Yeah.
What is my a value? My b value is right about there. So b is going to be the 14.7 number, and if you can, use the exact value from your calculator. The c value in the quadratic formula.
0.
Good, 0, yeah. So let's try writing it out. I'll do my best. Negative b plus or minus square root of b squared minus 4ac. Well, that's not bad. All over 2a. Negative 14.7 plus or minus 14.7 squared minus 4. Negative 4.905 times 0 all over 2 times negative 4.905. I'm sorry it's a mess up there. Are you able to understand what I'm saying though? At least verbally? I'm gonna see if I can try to find a way to fix this while you guys do the quadratic formula. And do the mouse function. Okay, one of your answers should be 0. Is that what you guys are getting? Yeah. Okay, let's talk through why should one of your answers be 0. We're asking you, when is the ball on the ground? Well, wasn't the ball basically on the ground as you kicked it? But the other answer will be when it comes back down to the ground again. So you probably have to use the second of the two answers to figure out how long it's in the air for. Problem is, this thing's not showing me an actual pen.
Oh, I didn't put the negative in
I think I might just have to suck it up for the rest of class, and then I'll try seeing if I can troubleshoot this later. Were you guys able to get an answer? It sounds like you guys are getting about 3. You guys get the same thing? Okay. Okay. Okay, so time was either 0 seconds or about 3. We got a couple sig digs though, so I do need a second sig dig. 3.0? Awesome. Everybody good with that? Alright, moving on. Alright, the last one we want to figure out is the horizontal distance the ball is going to travel. Now that we know how long the ball is in the air for, that should help us figure out how far it's going to travel. So let's see if I can draw on this picture here. We now know the ball is going to be in the air for 3 seconds. So knowing that information, if I want to try to find this distance here, it's really, pardon me, it's just the formula of velocity equals distance over time. I'm going to use a new slide here. So velocity in the x direction. Why is it working now? I can see the pen. Velocity in the x direction will be equal to the distance in the x direction divided by time. We know the velocity in the x direction, though, right? Didn't we calculate that way back in step 1? Right? The x component of this was somewhere back here. Right, where did we do that? I know we did this somewhere before. Just my work's a mess. 8.5. Can you guys see my issue here? Look, now the pen is showing up. Right? So like now I can see where I'm writing. Right? But before, the pen was not there. This is driving me nuts. So anyways, just so you're wondering why I'm so frustrated. Anyways, 8.5. That number, hopefully we can go up in our calculator and find it, because that's the velocity. This thing was always traveling in a forward direction. So 8.5 whatever meters per second.
It's just 8.5.
It was just straight up 8.5? Oh, okay. Distance in the x direction. You guys found time, right? You said it was 3.0, but was it like 3.0 something?
0, 0.
Oh. Sure, whatever, right? 0, 0, 1, 5, 1. So times it up there, and you got your answer. Does that make sense? I hope it makes sense. I'm sorry if it doesn't. We'll have to chat more later. I'm not being nearly as neat as I'd like to be today. So roughly that looks like it's going to travel 8 times, I don't know, 26 meters maybe? 25. But we only get 2 sig digs. Nice. Okay, so I guessed it. Alright, let's talk through that example one more time, because there were a lot of little things that I want to make sure you're clear on. So instead of me to write to talk through these ones here. How do you find a horizontal and vertical component? You have to use trigonometry. You're going to use sine and cosine. If I give you the speed of 17 meters per second, that's the hypotenuse, or the resultant. So like as he kicks the ball, As he kicks the ball, that's the trajectory like on the hypotenuse. So we use trigonometry to break it up into an initial x and y velocity. If it ever asks you for a maximum height implies that the y velocity final is 0. If it ever asks you for the length of time the ball will be in the air for, that's going to mean that your distance is probably going to be 0 in the y direction, because it's gone all the way up and all the way back down. That makes sense. This one right here is usually pretty useful, because once you find time, then time can be useful for the x direction stuff. So one more time. If you ever want the maximum height of a ball, the final velocity in y is 0. If you want to know how long the ball will be in the air for, use the amount of distance it's going to travel. It's essentially traveled no distance in the y direction, because it started on the ground and ended on the ground. The horizontal distance, that's going to depend on time, so you probably have to solve C before you get to D. This is going to be our lab next week, Monday. What we're going to do in our lab is I'm going to stand on top of a ladder, something a little bit higher up here. So I'm going to stand on a ladder. And I'm going to shoot our Nerf gun into the air. So I can't draw a gun very well, but pretend that's our Nerf gun. What I'm going to do is I'm going to measure the angle at which, yes, I'm going to measure the angle at which we're going to launch this thing. And I'm going to shoot a projectile until it lands. What we're going to do is we're going to measure the distance that it traveled for in the x direction, and we're going to measure the time that it was in the air for. And those are the only things we can measure, really. But we can work backwards. So basically take the exact same scenario we just did, and we're going to work backwards, and we're going to try to calculate the velocity resultant of the gun. Let's talk through how we do that. If I know the distance it travels in the x direction and the time it travels in the x direction, I should be able to calculate the velocity in the x direction. That makes sense? We're just working backwards. Well, if I were to draw a little triangle in here, if I have the velocity in the x direction and I have the angle of, let's say, 30 degrees, that should allow me to calculate the hypotenuse using cosine. We're then going to calculate some other things. Knowing this 30 degrees and velocity x, I should be able to calculate velocity y using tan, because that'll be opposite over adjacent. So now I'll know the velocity y. But don't forget, I still know time. And I know the acceleration, because it's gravity. Well, based on that, I should be able to figure out the distance the ball goes up into the air for. But the other reason why I would have known that anyways is because the velocity final in the y direction at this point would have been 0 as well. So we can also calculate how high the ball was going to travel. We have no ability to measure how high the dart is going to go, because there's no way I can actually have one of you stand like on top of the roof and like figure out how high it is. But using our calculations, we should be able to tell what the total distance it would have been up there was. Does that make sense? Okay. Let's try our next examples here. Okay, the pen is showing up again here. Maybe this won't be so bad now. So, scenario here, you're going to throw a rock off of a cliff at a velocity at an angle. So this is kind of similar to the punter question, but now the difference is you are now standing on top of a ledge. This ledge is 15 meters high. And you are going to throw the rock like that. Oh, no, I can't see the thing again. I spoke too soon. Let's see it again. All right, well, we're back to me not being able to see what I'm drawing. Okay, if I'm going to draw a triangle, right about here, there we go. If I were to draw a triangle in right here, 20 degrees is going right here. And the velocity at which I actually throw it, so the hypotenuse velocity, would be 8 meters per second. Somewhere sitting in there. So let's try some of the same things here. Before I even get to part A, part B, part C, what I really should do is break this triangle up into a velocity in the x direction, a velocity initial in the y direction, based on the 20 degrees in the corner and the 8 meters per second right here. You guys think you could find the velocity x and the velocity initial y using sine and cosine? I skip some steps for writing here since that's hard for me here. So basically what you need to do is you need to write out sine of 20 is equal to VIY over 8, just times up the 8. VIY and VX. And let's see if we can find these values here. Big yawn. So the y one is going to be involving sine of 20 times 8, and the x one is cosine of 20 times 8. Oh. I can actually get these ones as well.
Wait, the sine?
The sine one is going to be for y, because it's going to be opposite over hypotenuse. And then the adjacent one, so x will be cosine. Did I say that right? So 8 times sine of 20. Okay, so I've got 2.736, oh my goodness, what's happening here? 16 repeated. 2.73616 or so. Is that what you guys got for the one?
Yeah.
Okay. And then 8 times the cosine of 20, 7.51, give or take. 7.5175. So far, so good. Okay, so let's take those values then. And we want to figure out, what did it ask for? The time the ball is going to, the rock is in the air for?
How long it takes it to fall.
How long it takes the rock to fall. So we're looking for time. So here's what we know. The velocity initial in the y direction, we have. We also know the acceleration in the y direction. It's negative 9.81 meters per second. You guys see what's happening here? Like halfway through, it's putting a purple squiggle in there. My hair over this.
Oh yeah.
Do you see that?
Yeah.
Okay. In this example here, we know one more thing. We know the distance the ball is going to travel. It's not going to be 0 though. In the y direction, the ball is going to travel negative 15 meters. Say that again. We know the distance the ball is going to travel in the y direction. It's going to go up, yes. It's going to come back down, and then it's going to go further down than when it started. So the distance in the y direction it's going to travel will be negative 15 meters. Does that make sense? Because basically it's dropping off a ledge. So based on that, we should have enough information now to solve for time. It stinks again though, because you're back to using the quadratic formula. Glad I taught you that and beat that into your heads over the last while. Okay, so let me see if I can write it out here nicely for you. It'll be d in the y direction equals vi in the y direction t plus 1/2 at squared. Let's see, about there maybe? No, there. Negative 15 is going to equal, let's see, what was our y direction? 2.736? 2.736 t plus 1/2 of negative 9.81 t squared. Okay, so rearranging this a little bit nicely, and don't forget that is a negative 9.81 if you can't see very nicely on mine. This is supposed to be a negative 9.81. So to rearrange this, you guys are probably way ahead of me anyways. You need negative 4.905 x squared. You need plus 2.736 x, and you're going to need a plus 15. Because the 15 is coming to the other side, right? Okay, so negative 2.736 plus or minus 2.736 squared minus 4, negative 4.905 and 15 all over 2 times negative 4.905. And go. Okay, so I need to go back up and save that number as A. A plus square root of A squared minus 4 minus 4.905 15 divided by 2 times 4. Okay, so the first one I got negative 1.5 when I solved that. Anybody else get a negative 1.5? I have a negative 1.5 when you solve. I can actually explain why you might get a negative value for time here. Just need to draw my picture back up a little bit more. We're looking for when the ball is going to be negative 15. Oh, there's a cursor again. Thank you. Okay, this is good fortune. We're looking for when the ball would be at negative 15. Well, in a way, imagine that you could go backwards in time. If this could be extended backwards to like here, it would have been down here at negative 15, but this would have been like at like a negative time amount. So we use the word extraneous solution sometimes. So if you got the negative number, negative 1.49, that one's not going to count. Do you guys get a second value? A positive one?
I got 2.67.
2.67? Anybody else?
I got.
I'll try mine again here. So negative A minus the square root of A squared minus 4 15 divided by bracket 2 times negative 4. Oh, shit. I got 2.04, 2.0497, something like that. Okay. 2.04976. Like, this is what I got. Some of you are getting that. Okay, let me come troubleshoot here. Oh,
I didn't see it. I was like,
yeah, I would remember even using like
I hate this so much.
even storing it as like a year or something like that. I would do that. So I'll take this value here. So we store it as A.
Can I just quit?
So then I can say negative A plus the square root of A squared minus 4 times negative 4.905.
Oh my god.
I'll divide that all by 2 times negative 4.905. So that's where I got the negative value, which is like kind of drop this graph backwards here. Does that make sense? So then I'll just redo this, and I'll redo it now for the negative.
Okay.
And then divide by 2 times negative 4.905. Okay, so you get that value there. That works. Okay. You guys.
I don't know why she didn't get it.
Okay, now you have A for this one. Okay, but you check in B, is that because B is what is B squared? Okay. It's not negative. When we wrote the equation, it was negative 15 on the side of the equation. But when we bring it to the other side, it's plus. Yeah, that's how things going to come there. So we'll do that. And we'll divide by 2 times negative 4.105. So this is the. So here, only, we missed a sign here. This is here negative. Right, because it's negative. Does that make sense? So basically, if we just flip this around, that's our answer. So now we're going So, is that value? So,
Doesn't go with
we did
my skin.
sign. So, that's okay. So, negative 8 minus square root a squared minus 4 minus 4.905 positive 50 divided by 2 times. You did that again. You need negative 4 points. 4.905. That work? Okay. Anybody else having issues that I can help troubleshoot before I go further? You're good? Okay. Not that I can do a ton of things here. How are you guys doing on this? Were you guys able to calculate the 2.05 number? Okay, that's good. Okay, what else do I got time for today? We're kind of hitting the end of class here. So then we can finish off this example, and I think we'll just have to call it a day for now. Okay, so we figured out how long it takes the rock to fall. That was a pain. But the good news is once we've calculated that length of time, most other things are not quite so bad. Okay. How far from the base of the cliff will it hit? Well, we're looking for this distance right here. I'll use a new color and it's right over top here. If I'm looking for this distance in x, from here to here, really that's velocity in x equals distance in x over time. Don't we have our x velocity? Didn't we calculate that a ways back? I think it's still sitting on my screen right here. It's the 7.51 number here. So take that, where am I trying to write here? The 7.51 number. That equals your distance in x over the time. And we just found that time was 2.05 kind of thing. Just times it up there. Does that make sense? I'm doing half of that verbally. Your velocity in x, we just found. I mean, we found it right at the beginning, right? It was the sine of, no, it was the cosine of 20 times 8. So 7.51. Take that velocity. It's always traveling that x speed. Times it by the time we just calculated, and there's your distance in x. Does that work? So take that answer and times by. I got 15.409, something along those lines. So with 2 sig digs, we should call it 15 meters. Does that make sense? Okay, last one. This is the hardest one, and then we're going to call it a day. Well, it's not the hardest one, but it's going to require one more thing. It asks for the velocity as it hits the ground. Here's the hardest part about the velocity when it hits the ground. You know how we started with a triangle? We have to finish with another triangle. Because really what's happening is when it hits the ground is it has an x component, it has a y component, and it's coming in at an angle. That's why it kind of stinks, because what we have to do is as it hits the ground, we need to know how much velocity final it has in the x direction, how much velocity final it has in the y direction, and we have to find that hypotenuse. Why did the purple just show up randomly there? So dumb. Does that make sense though, what we have to accomplish? Okay, good news, bad news. Good news, we already know the velocity in the x direction, because it's always the same thing, right? So whatever it was, 7.5175, that's what I have written down. 7.5175, right? That x velocity that we've been using is still that number. The downside is I have to find my velocity final in y. But here's the good news. I know almost all of my y values. I know the acceleration in y is negative 9.81 meters per second. I also know the distance we're going to travel in y. It's negative 15 meters. Just 15 meters. Yeah, ignore that. I also know the amount of time it's going to travel for. It's traveling for 2.05 seconds or so. Hey, that's 3. That's enough. But guess what? I even know the last one. I also even knew the velocity initial in y. Because the velocity initial in y was... It's a mess on here. I'm so sorry, guys. The initial velocity in y was this one down here, the 2.736 number. So velocity initial was 2.736 meters per second. So I don't care how you find the velocity final in y, but you have all of these values here. Pick a formula. Any formula will work, right? You could pick the one involving a, dy, t, and v final. You could pick dy, t, a, and v final. It really doesn't matter. But find a formula and find the velocity final in y. If you find this velocity final in y, use Pythagoras' theorem to calculate the resultant. So I'll try to do one here. I know the bell is going to ring for those guys there in a second, but it will look something maybe like this. Velocity final squared equals velocity initial squared plus 2AD. I know the velocity. Let's get the bell's going to go. Stop ringing. Okay, one more time. Throw this board. Actually, no, I can't because I need to return it. It has a mind of its own. It just all of a sudden starts changing colors on me. Okay. Plus 2AD. Velocity final, no. Velocity final is what we're looking for. Ignore that mess there. Velocity initial would have been 2.736. That's negative 9.81. You also need a minus 15 in there. Anyways, you guys can handle this? I'm so sorry. It's a mess today. So 2.736 squared.
17.6.
Do you have an answer for me? Okay, that's probably just the best, right? Anybody else get 17.6 for your velocity final? 17.37?
Why is the 15 negative?
Because you're going down 15 feet, right? The acceleration is pulling you down, your distance is pulling you down, but if you use an initial velocity, your initial velocity was pulling you up. Okay, minus, I guess you have something. We'll look at yours in a bit. Is everybody else on a consensus of what the velocity final in y is though? 17.36? Okay. If you agree that, where would this be? This would be 17.36. square that, add it, and square root the whole thing. And you got your answer. And I think it's time to pack up. Good idea.
Tasha, red young man, can you please come to the office? Tasha, please come to the office.
It really looks like a little child scribbled all over my board.
What two
I'm
numbers?
so embarrassed.
Just do it.
What was that?
What two numbers am I squaring?
Yeah.
So you need to take the velocity final you just found in the y direction,
Yeah.
and then you need to take the velocity of the x direction, which we calculated way back when.
Okay.
Right? And those are, I'll just stand up here because my board sucks, right? It's going this way with the same constant speed. It's going to be hitting at an impact. Find that resultant. Right. One last thought before, I know I'm going to lose you guys over here, and I'm sorry if today was a mess for you. I would recommend one of the two strategies. Whenever you get a value, you need to obviously organize your workday way better than I am here, because I have no ability to right now. But you need to organize things. I would like say once you find a value that you know you're going to use again, like time or velocity initial x or y, I would write it in the corner with every digit you can, and I would like say circle it so that you can use it again later. I would also store it in your calculator, because clearly you can see like you are going to be reusing these numbers over and over and over again. Okay. Okay, sorry guys, I hope that wasn't horrible for you. I will try to make corrections if I need to. And I'm going to buy a new board again. So, we'll see you later. Okay, for you guys, tomorrow I'm actually not here. I'm on a dentist appointment. So tomorrow's a work day. And we're done our unit. So, going forward from here, you have a lot of stuff to do now. So, yay for you guys. There's 2 assignments. Hopefully you're done more or less the first one and they're starting the second one. Then there's the Mythbusters project, a paper. One of those you can just choose not to do. And then next week we've got a lab on Monday, a quiz on Tuesday, a workday Wednesday, and a test on Thursday. Okay, quick thoughts here. I had always thought that it would be better to get it over before Thanksgiving. If you guys need to bail on that plan, let me know next week, because we can push it back.
Can we just do the test before, but like have everything, like the paper?
I can do that. I can do that. Is that a good plan? Because honestly, like, my normal plans would have had at least 1, maybe 2 extra days of work time. It's just it felt so natural to try to finish it before Thanksgiving. So if you want to, I can adjust the plans. We can write the test after Thanksgiving if you want. We could just write it beforehand and make the stuff due afterwards. You like that best? Okay. I'm good with that.
What's happening on Wednesday?
On Wednesday. Next week? Workday. So is that plan then works? We'll do workday tomorrow. Granted, I'm not here, but work on something, right? You have a sub.
Is the sub gonna know what we're doing?
I have no idea. Maybe. Monday we're doing a lab, Tuesday a quiz, Wednesday a workday, Thursday a unit test, and then we'll just make everything due after we come back from Thanksgiving. That works with you guys? Okay. Guys, if you do want to write the test afterwards, we can make that work too. Okay. So if you're feeling like you want an extra couple of days, we can do that too. Okay. I did skip an example, right?
Yeah.
Okay. If you get a chance, maybe tomorrow, why don't you guys as a group see whether you can try that last example without me? And then maybe on Monday, we'll see whether we got it right. And in the meantime, I'm going to try to troubleshoot this stupid thing and see whether I can make it work better. Because this is not, this won't work going forward. It's crazy. Goodness.